Self-driving cars are becoming a reality in front of our eyes, and machine learning is at the heart of it all. An ongoing challenge in this pursuit is that vehicles must interface with our physical world. They need to understand and abide by the same signage and traffic rules as all human drivers on the road. There are over 500 official road signs in the US alone. Confidently and quickly recognizing them all could mean the difference between a successful ride and a deadly one. Quantum computers can help improve machine learning models for image recognition, as demonstrated in IonQ's collaboration with Hyundai. But how does it work? Let's consider a simple case of two common road signs. We start by loading training images onto a quantum system to optimize the machine learning model. As we entangle qubits, we form a data storage space through the various combinations of superpositions. This data space doubles with each new entangled qubit. When we entangle 8 qubits, the data space can hold 256 unique values, which is enough for a small image, 16 by 16 pixels. If we double the entangled qubits, the data space can now store 65,000 pixels. With 24 entangled qubits, the quantum system can store 16 million pixels, or an image 4,000 pixels on each side. By comparison, an image that size would require about 32 million bytes of storage on a classical computer. Quantum systems grow exponentially and become very powerful. Even a simple entangled system can improve machine learning. With only 8 qubits, we could hold a compressed version of the training images, 16 by 16 pixels in size. Surprisingly, we can already start seeing the power of quantum at this small scale. Here's how. Loading an image means simply copying the values of each grayscale pixel to its corresponding superposition spot. After loading, the quantum system holds the compressed training image. Now that we understand how loading a single image works, we can gather a collection of well-labeled training images. The image recognition algorithm transforms each image using a quantum model that depends on a small set of input parameters. We begin the process by selecting random values as input parameters. As the quantum operations, controlled by the input parameters, are applied to an image, the input parameters trigger transformations in the entangled system, impacting neighboring pixels and shifting patterns around. By the end, the entire quantum system can be summed up by a single output value. But this value doesn't mean anything until we compare it to the labeled images. The training process requires the application of these input parameters across the entire training set of images. The algorithm loads each image separately, applies the transformation, and reads its output value. Initially, we expect these output values to seem random. Then, the algorithm starts adjusting the input parameters, paying careful attention to the output values and looking for early correlation with the image labels. With each iteration, the quantum system produces different output values as the input parameters are adjusted. With each iteration, we start to see these values diverge between the different classes of images. The input parameters continue to adjust according to the results, until we have differentiated groups of results that correlate to the known labels. Based on the results, after several hundred iterations, we now recognize one end of the output spectrum as a stop sign and the other as a no-entry sign. Now we are confident that with these input parameters, the quantum model produces output values that distinguish between the two classes of images. This is the learning part in machine learning, but quantum requires far fewer parameters. This iterative algorithm is a hybrid process. Some of it is performed in quantum and some uses classical computing. The classical computing resources are used for data storage, any pre-processing of data such as scaling, and selecting the input parameters. Once the data and input parameters are provided, the quantum computer stores the data in quantum states, handles all of the parallel transformations, and produces the final output value. The classical side evaluates the output values, which closes the loop by selecting the input parameters for the next iteration. Our example demonstrates a few key advantages of quantum computing in image recognition using machine learning. In the entangled system, transformations occur in parallel across all desired pixels, regardless of quantity. There are types of transformations that classical computing can't perform, and they lead to new insights about the training images. Each new qubit doubles the size of the computational data space. We can use this expanded storage and computation space to increase the resolution of the training images, or to maintain multiple copies of each image so the system can explore different structures and features that emerge with different transformations. And it does it all in parallel. Finally, quantum models can produce the same or superior results with far fewer input parameters, which could greatly reduce the resulting size of the model, making it far more efficient. IonQ expects that when we cross 40 high-performing qubits, this quantum algorithm will be able to explore image recognition transformations that are otherwise impractical using classical computing. When we reach 64 qubits, this quantum algorithm is expected to produce superior results to classical machine learning algorithms using classical solutions. Future image recognition applications will need to scale up and be extremely reliable yet simplified. Quantum machine learning is one of the most promising paths for achieving this goal. Not only can it help self-driving cars recognize signs, but it has the potential to advance a vast range of industries. Quantum machine learning can help with everything from adding automation to manufacturing and agriculture, improving healthcare outcomes and discoveries, introducing retail and logistics efficiencies, identifying security and defense threats, and making transportation safer. Visit ionq.com/QMLDemo1 to discover more about image recognition and quantum machine learning.